Have you ever wondered why a baseball flies in a clean arc, yet an electron acts like it can be in two places at once? Why the world you touch feels so predictable, but the world underneath behaves like it's playing by an entirely different rulebook? Today, we're diving into the strange borderland where everyday physics ends and quantum physics begins. Hey everyone, welcome back to the channel. If you love exploring the mysteries of the universe, you're in the right place. Before we jump in, make sure to hit that like button, subscribe, and turn on notifications so you don't miss any future deep dives into science and reality. And if you've ever had your mind blown by a physics fact, let me know in the comments. The world of classical physics. Let's start with what we know best, classical physics. This is the physics of Isaac Newton, falling apples, orbiting planets, and the way your car speeds up when you hit the gas. Classical physics works beautifully for things that are big, slow, and visible, objects you could pick up, throw, ride, or see through a telescope. In this world, objects have definite positions and velocities. A ball is here or there, moving at a predictable speed, and if you know its initial conditions, you can calculate exactly where it will go. In classical physics, nature is like a well-oiled machine, deterministic, predictable, and logical. Enter quantum physics. The rules change, but shrink down far enough into atoms, electrons, and photons, and the classical rulebook falls apart. Quantum physics takes over, and here things get weird. Particles don't behave like tiny billiard balls. Instead, they act like waves and particles at the same time. Their position isn't definite until we measure it. It's smeared out, described by a probability cloud. Instead of certainty, quantum physics deals in probabilities. You can't predict exactly where an electron is, you can only predict the chances of finding it in a particular place. Deterministic versus probabilistic. This is one of the biggest differences. Classical physics says, given enough information, I can tell you exactly what will happen. Quantum physics says, even with all the information in the universe, I can only give you probabilities. It's not that we don't know enough. Nature itself doesn't allow certainty at quantum scales. The measurement problem. Another striking difference is measurement. In classical physics, measuring something doesn't change it. You can check a thermometer without changing the temperature of the room. Quantum physics? Not so much. Measuring a particle forces it into a specific state. The act of observing fundamentally changes what's being observed. This is the notorious observer effect. Why both are true. So which one is correct? Classical or quantum physics? The surprising answer, both. Quantum physics rules the tiny world, but when billions of particles come together, their quantum weirdness averages out, giving us the classical world we experience every day. Think of classical physics as the zoomed-out version of quantum physics. Not wrong, just a simplified picture. Why it matters. This difference isn't just theoretical. Quantum physics powers modern technology, lasers, MRI machines, GPS, computer chips, and even the coming wave of quantum computers. The weirdness of the quantum world is the reason your smartphone works. So, there you have it. The difference between the predictable universe of classical physics and the probability-driven world of quantum physics. One describes the world we see, the other describes the world that makes everything possible. If you enjoyed this journey into the foundations of reality, hit that like button, subscribe for more mind-expanding content, and drop a comment telling me which part of quantum physics blows your mind the most. Thanks for watching, and stay curious.